So our next work in progress will be presented by Chris Thames from Williams and Mary.
Good afternoon. All right, let me get mine up. All right. Good afternoon. Yeah, my name is Chris Thames. I'm a PhD student at William and Mary, working with Dr. Yifan. And we're working on trying to understand a wafer-scale GPU performance with an architectural simulator that we've been working on. Just kind of a quick agenda of what I'm going to talk about here. We'll go through the background of wafer-scale just for a little bit. The methodology we've used, the results that we've gotten right now, implications of that work, some future work that we're planning to go forward with on all this, and then a conclusion. So talking a little bit about the background of wafer-scale. So the idea behind wafer-scale was a big idea back in the 70s and 80s. They attempted to build some wafer-scale systems at the time, like this one by Trilogy Systems, but they failed at the time. The technology just wasn't there for these types of systems for building a system on a single wafer. Since then, there's been a lot of technological advancements. Today we do have multi-CPU, multi-GPU systems out there. The introduction of the silicon interconnect fabric has helped to be able to connect these systems together on a wafer. And there's even a couple of companies out there, Cerebras, who's working on wafer-scale engines, like the one you see here on the right, and Light Matter, that's working on a system called Interconnect Passage. But all of these hardware and electrical advances have just come in the last few years, or really in about the last year or two. But there's not been a lot of work done in terms of the performance characteristics of these systems since they're not in regular use. So that's kind of where our focus was to kind of look at this to try to understand the behavior of programs on these types of systems. So the methodology we use, so we started with MGPU Sim, which already exists out there to do multi-GPU simulations. And basically we extended that with this wafer-scale mesh network of switches, and we'll talk more about that on the next slide. But basically we're just using GPUs that have 4 compute units. They have vector, scalar, and instruction L1 caches, L2 cache, and 4 gigabytes of HBM. The simulations allow either a single or multiple CPUs, and then we have an IO memory management unit. But if you look here, so this is basically a 5x5 mesh. That one of the ones that we simulated. We did 2x2 meshes, 3x3, 5x5, and 9x9. And with those, basically we placed a CPU in the corner at the 0, 0 node, and GPUs at all of the other nodes, as you can see here. We also did, though, look at specifically with the 5x5, we were wondering about placement of CPU. So we tried putting the CPU in the center node at the 2x2 point to see how that would affect things. And then as well, we tried a 4 CPU version where we put the CPUs at 1, 1, 1, 3, 3, 3, 1, and 3, 3. So basically, when we did just the 2x2, 3x3, 5x5, and 9x9 with the corner CPU, what you can kind of see here is that we do see improvement as you go from 2x2, 3x3, 5x5. You see improved performance as we go along. Notably, in most cases, it's not a linear improvement. So just doubling your CPUs or GPUs doesn't necessarily give you double your performance. But even more notable on top of that, or addition to that, is you'll notice with the 9x9, while we saw improvements in the fast Walsh transform benchmark and the matrix multiplication benchmark that it actually had a negative impact on our performance for most of the benchmarks. So it made it kind of clear that just adding more GPUs did not necessarily give you improved performance with it. The other thing that was notable about all of this is that it was clear that there's no one simple solution as to how you lay things out to get optimal performance for all problems. That the problems that you're trying to solve can be significantly different and can require different organizations of the mesh network. And then this was basically where I talked about that in addition to just looking at the 5x5 with the corner CPU, we were curious to see how it would do with moving the CPU to the center, more centralized located, or with 4 CPUs. That the most notable thing from the data that we see was that there was a minimal performance impact, that regardless of where we placed the CPU or the number of CPUs, it didn't have a significant impact. There were minor ups and downs. Probably the most notable there being the fast Walsh transform, where you notice that there's a decline in performance. Most likely, if you recall, that was one that did perform better with a 9x9. So it seems to be heavily dependent on the number of GPUs. So by putting 4 CPUs, you basically took away GPUs and you saw a decline in the performance. But for the most part, there was no significant improvement to be had from this, what we did here. So one thing we did, we wanted to dig a little bit further into to trying to understand what was going on with some of the behaviors in the system. And so we looked at the RDMA transactions with the GPUs, with the 9x9 mesh in this particular case here. And you can kind of notice that on the fast Walsh transform in the left side here, you can see it's pretty uniform. I mean, there's about a 10% variance between different GPUs, but basically the incoming and outgoing transactions are in the same ballpark as each other. But notably, you'll notice on the matrix multiplication, while most of the GPUs have a pretty uniform distribution, you know, there's 3 on the front end and 1 at the back end that had a order of magnitude, in some cases higher, in terms of the incoming transactions. So the other thing that became clear here was that you can have these problems with peaks in these transactions and potential bottlenecks that can exist depending on the types of problems that you're trying to solve here. So looking at kind of the implications of what we see here is that, yeah, I mean, as we increase our capability, as we increase the number of GPUs that we have in these types of systems, it also increases the complexity of the problem of trying to understand what you're going to see performance-wise for different types of problems. As I said, there's no single mesh architecture that's going to be optimal for all of the problems that you might be trying to run on these wafer-scale systems, as well as that you can't necessarily expect to have linear scalability in these problems as well. That just by doubling your GPUs, you're not going to double your performance. And then the third thing being the fact that, yeah, there is the potential for data bottlenecks when you're working on these large scale systems. So kind of where we're going with future work. We're looking basically to do a more thorough study of some of this performance work. So there's other benchmarks that we're looking at larger problem sizes. Definitely want to try to work towards larger GPUs out there, kind of more on the order of what you see in some of the ones that are being built right now. The simulation doesn't really restrict the number that you can put in it. It's just basically the performance of the host and what it can handle. Basically looking at the placement for memory and computational threads in the system, considering some of the geospatial features of it and the NUMA effects of the system. And then looking at spatial division of some of these massive things, the massive GPUs. One of the big things that did strike us as we were kind of looking at some of this stuff is that, yeah, if you can get better performance for a specific problem out of a 5x5 mesh than you can out of the 9x9 mesh, but you've got a 9x9 that you want to work with, then clearly you can multitask on that wafer scale. If you can come up with a distribution that makes sense on that system to run multiple tasks, either from the same unit or the same user, or from multiple tenants as well, basically, and using shared resources. So, in conclusion, basically, like I say, we were looking at trying to understand a little bit better in the performance characterization of wafer-scale GPUs. One of the things that's clear already in the work that we're doing is that, yeah, that more computing resources does not necessarily equate to higher computing performance. And that different workloads will have different optimal allocations, and we want to try to get a better understanding of what works well for different types of problems that you're trying to solve. And then some of the challenges that we're still working with is, like we talked about, the placement of where data is stored on these systems, of the execution of threads within the mesh, and then whether we can do better spatial division so that we can get improved utilization on some of these large scale systems. And so that's my presentation. So thanks. And if you have any questions, I'll take them in my emails here if you have any questions after.
Thank you so much, Chris. There is one question in the chat.
Okay.
Can wafer-scale GPUs be designed to tolerate yield issues? And can process variation impact design of wafer-scale GPUs?
I would say the answer is yes, that you can, but that's exactly part of what we're trying to understand, you know, is you know, what are when we talk about handling some of the memory issues, the data issues, in terms of how we can spread data. And it's part of what we were trying to understand when we were looking at the multiple CPUs too, is the fact that can we distribute some of this to deal with some of the yield problems that you can you kind of manage it? And there may be still more to do. It's still early work in terms of what we've done with it. We haven't tried to do a lot of optimization. We've kind of just looked at what's the performance of the existing system that we have right now. So yeah, I mean, I do think there is certainly is potential for designing around yield problems, but yeah, we've still got to look into that.
And one more question in the chat.
Is it open source? At this point, we don't really have it out there. It's not. It's still, there's still work to be done on it, I think, before we would make it public at this point in time. One of the good examples is basically like where we're doing this work of doing the central, moving a CPU to the center, or doing multiple CPUs in it. It's not well optimized for that right now in terms of being able to reconfigure it. So we're still doing some work with that, but I definitely believe it definitely will eventually be open source once we get it far enough along.
Thank you. Are there any more questions? All right. Thank you so much, Chris.
Thank you.